Hello and welcome to this episode of Thermonuclear Takes from Physical Attraction. Now, I know you're a pretty loyal bunch in general, but just in case anyone is listening to the show for the first time, Thermonuclear Takes episodes are an episode format we have which is a bit more informal than regular episodes. We use them as an opportunity to go over interesting stories which are related to topics we've previously covered on the show or which don't quite fit into their own unique episode. Also to respond to any listener emails and to give general updates on the state of the show. So for this reason, the script is a bit more informal, although I have written 20,000 words for this one. There's less in-depth analysis, it's a little more topical and a little more timeless than our usual shows. And as I just mentioned, this one has gone long enough that I'll split it into 4 episodes, which will come out over the next couple of weeks. All of this is to say, if this is your first episode, you might want to listen to something different, and indeed, you can go to the website, physicspodcast.com, and we have there an About section which has a long list of all of the episodes, a sort of full episode guide for the over 200 episodes that we've produced so far. And that's amazingly over 200 episodes, thanks to everyone who has listened and supported the show and helped me to get to this point, sending your emails, sending financial support. Frankly, I still can't quite believe we managed this. I mean, when I first started this, my idol was Mike Duncan from the History of Rome podcast, and I couldn't believe that anyone would be able to put out as many episodes as he has in that History of Rome podcast, and we've surpassed that, so thank you so much for supporting the show. I do appreciate it. And of course, you already know what you can do if you want to help us further. Tell folks about interesting episodes they might want to listen to, Patreon, blah blah blah, you know the score. So the quick show update at the start then. This has actually been the first time I've worked on a script for many weeks because my day-to-day life has got incredibly busy. Without getting into too much detail, probably the busiest and most transitional things have been for as long as I can remember. Long hours, lots of other commitments and so on. When it's hard to set aside a big chunk of time every week for scripting and writing, it's difficult to make progress. I drift out of being able to research and script things in a way that's much easier when I'm immersed in the space of the topic that we're covering. And unfortunately, I do anticipate that pressure on my free time is going to carry on for the next few months at least. Now, we had a hiatus recently, but I don't want to make a habit of that, as I think dropping out for this indeterminate period of time is difficult for listeners. I have a few months of episodes pre-recorded ready to go, which Patreon listeners will have heard already. What may end up happening is we might switch for a bit to bi-weekly episodes for a little while. I would prefer to give you at least a consistent stream of stuff while we get over this busy patch, even if it's less frequent. So that's not going to happen just yet, but if it does happen, I'll be sure to let you know. The other thing to note is that I'm currently releasing this series of episodes on cosmology, but this series is not fully written and recorded yet. So my priority for the time I do have will be to try and finish writing that series so that I can get the second half of it out. But it looks likely I won't finish in time, in which case I'm simply going to have to split that series into 2 parts and switch over to some climate episodes that I've recorded already. Now I realise that this is a bit annoying because we've got this grand cosmological narrative. I would have preferred to avoid it. The plan was to avoid it. I haven't been able to avoid it. And I think it's better to take a break from the series rather than forcing myself to crank out the second half as a whole bunch of substandard, rushed episodes just to finish it off, so that I can tell the story properly. Again, I do realise that this can be quite annoying for listeners. I apologise for that. It takes a lot of time and effort to produce this. Life circumstances don't always permit exactly what I'd like to do. And, there were equally a lot of times when I was able to produce multiple episodes a week, which we had recently, especially at the start of COVID. So in the grand scheme of things, I think it does balance out. But I'd like to thank everyone again for your patience. Finally, on that note, I wanted to reflect a little on some of the recent episodes we did on cosmology. Part of this is another apology. I referred in those episodes to some slides and a YouTube video I'd hoped to create for the Friedmann-Robertson-Lemaitre-Walker equations, so that I could explain those equations to you with some graphs. As yet, that hasn't happened, which I profusely apologise for. That's one lesson for me, is to do stuff when I'm writing that I'm doing the stuff, rather than saying that some future version of me will sort it out, because it isn't always going to work out that way. But the idea is still there, and when that comes out, perhaps with the second half of the cosmology series, I'll let you guys know where to find that on our YouTube channel. Now, some other things on cosmology, we had some feedback. One of the great things about doing this show is that lots, if not most of the people listening, know lots about the subjects already, often more than me, and so the feedback I get is very high class. And there was one particular piece from a friend of the show, who was noted when I was going through the list of horizons in the episode on the edge of the universe, there were some concerns. For a start, this friend didn't like the Hubble horizon, which wasn't really physical, because the other horizons that we dealt with, the definition is based on causality. In a relativistic framework, this is the way we're used to thinking of, is horizons are about events in future space-time that you can influence, and events that can influence you from other regions of space-time, and those sort of determine the horizons that you're interested in. The Hubble is sort of a length scale, it's sort of a horizon scale that gives a sort of rough estimate for the scale of the size of the universe, but it's not actually motivated by any particular physics. So I could see why he was saying that that probably wasn't the best thing for us to do. And there was another nitpick related to this as well, which is also relativistic. And this is about the concept of now. There is no unique now in a general relativistic compliant world. Instead, the closest you can say to defining now is to talk about the Weyl set of hypersurfaces, which is the set of hypersurfaces that have a homogeneous density at all times. So the reason that this is relevant is that I had talked about some of these horizons and defining them in terms of saying, okay, well, beyond this horizon, light that some galaxies might be emitting now won't reach us. But of course, it's very difficult to define what you mean by now in a relativistically compliant world, because there's no universal now, no universal moment that is happening simultaneously in some galaxy way off in the distance that we can all agree upon. So the best I can say is that this is a mix of a genuine error and an oversimplification. So everyone, when you go back and you heard me say now, please remember that relativity dispenses with this concept of a single universal now, or indeed any frame of reference or inert background relative to which there is a now that makes sense to talk about. Instead, please insert a more appropriate explanation that reflects the nature of our glorious and complex universe. I am just joshing a bit here, but the point is well taken, and I think it's generally true of physics to say that learning physics is essentially learning how the universe is, convincing yourself eventually that yes, that explanation does make sense, and then later being told, actually, technically, what you just learned, that was an analogy, it was a simplification. Here's what's really going on under the curtain. And there's so many curtains that get drawn back as you get more and more into these topics. This happens over and over and over again. And indeed, perhaps one day we will discover that many of the theories we have now are just analogies or limited corners of more subtle and fundamental theories. This means that despite the reputation of physics as a subject where you're either right or wrong, there are in fact many ways of being wrongly right and rightly wrong. This is not me saying that I was right all along, to refer to light being emitted now in a faraway galaxy, but just to say that at best in this game you can aspire to being not even wrong. In writing this show, it's tricky to know sometimes which rung on the ladder of analogy to pitch things at, and this is made even harder when sometimes I'm not even at the top of that ladder myself and learning along with you to try and produce something that makes sense and is as accurate as possible. It's certainly true that a fully in-depth and technically correct explanation of cosmology would require us to have spent much more time on general relativity than we have done to date. And indeed, in lots of these cases, you end up dealing with what the sort of Copenhagen interpretation of quantum mechanics talks about as like the shut up and calculate approach, which is the most complete possible description of the universe we can provide. Is not even an analogy that exists in words. It's not even something that matches our physical intuitions of things that are based on how we observe the sort of mesoscopic universe around us, right? The most accurate description you can make of the system is with the mathematics. The problem is that I can't do the mathematics in this podcast format, and then when I try and think of a clever way to get around and do some of the mathematics, I forget to do it. So that's where we are with that. And I think if you the solution to this is just going to be to say, if you hear me say something that sounds egregiously wrong to you, absolutely let me know, and I will comment on it, especially for the places where this simplification spills over into inaccuracy, because I don't want that. And I hope that helps. On a similar note, listener Matthias wrote to point out that in one episode I also described how the expansion of the universe and of empty space would entail the average human getting 600 nanometers taller across the course of their lifespan. Now, not to be splitting a distance much, much thinner than hairs, but he objected to this on the grounds that the expansion this expands objects that aren't gravitationally bound together. So it applies to things like the distance between galaxies that aren't gravitationally bound. But obviously, the rate of this expansion is so minuscule as to be easily counteracted by gravity and other bonds like chemical bonds. And I think this is probably valid as an objection. I think this would be true of humans as well. So it's probably better not to think of it as a physical stretch in your height, as I may have described it, but instead as an analogy explaining how this rate of expansion, it's relatively small across small distances, but when you get to these distances of light years and kiloparsecs and 10 to the 10 metres and all this stuff, it obviously becomes much more important across these whacking great interstellar distances. So again, if you feel inadequate about your height, please invest in heels or stilts. Do not wait for the natural expansion of the universe to make you taller. I think that is advice I am very confident about giving. Okay, enough of this editorial stuff. Let's get into the topics that I wanted to cover with these thermonuclear takes. So the first thing I wanted to talk about was to briefly explain and contextualise as best as I can a few of the pure high-energy physics stories that have been in the news lately. This is a bit of a change of pace and climate change in cosmology, so me included, that's a change of pace for, so if I make any mistakes again, I can only apologise. Please ring in with your corrections and they'll probably feature on a future show. But we'll start with some context. I think the key context for these stories to understand was in our long ago series on particle physics, Concealing a Hadron, which you can find from the archives a few years back. Now, essentially, one way of looking at how physics progresses, especially this sort of high energy and theoretical physics, is as an interplay between theorists and experimentalists. Sometimes the interplay is clear. A new experiment will upend existing theory, and new theories then have to be developed to explain the results from that particular experiment. A classic example here comes from historical investigations into the nature of light. Thomas Young's famous double-slit experiment, which appeared to show how light could behave like a wave, as patterns of light passing through two adjacent slits could interfere constructively and destructively with each other, like water ripples on a pond producing an interference pattern. Well, that experiment was first performed in the early 1800s. Then later on, you had experiments that dealt with the photoelectric effect. This is shining light at particular surfaces, releasing electrons. This was explored extensively in the early 1900s by Einstein and others, and it appeared to show evidence for light behaving as particles. It could be explained well if you could imagine a particle of light bashing into an electron, transferring its energy, knocking it off the atom. This is where we get into this idea of wave-particle duality, light sometimes behaving like a wave, sometimes behaving like a particle, and this confusion over the nature of light, which, by the way, needn't necessarily behave like either of those things, it can behave like both. It was in part to explain that the quantum theory was developed, mostly in the 1920s. So in this case, for our broader theory of physical developments, experimentalists came up with confusing, contradictory results that were later explained by theorists. Now, this is the feedback loop where the experimentalists come back into it, because these new theories then, ideally, make other testable predictions, and you can use those testable predictions, you can set up an experiment that will confirm that the theory is true. So sometimes the cycle starts the other way around, right? The theory rides ahead of the experiment, and then the experiments attempt to confirm or disprove that theory. You can think of this for, say, the Michelson-Morley experiment, which cast doubt on the idea that light waves travelled through an ether-like background substance. This was the idea of, if light's a wave, then what is waving? There must be some luminiferous ether, they thought, that permeates the entire universe, which is carrying these light waves. And the Michelson-Morley experiment was one of the ones that gave pretty conclusive evidence that there was no ether. Or, more recently, you can think of the Large Hadron Collider itself. The most famous result that they came out with was demonstrating the discovery of the Higgs boson in 2012, but this in turn was only really confirming the theories surrounding the existence of the Higgs particle, which go back to the 1960s. Ideally, physics needs this interplay of experiment, observation and theory to constantly be in motion and feeding into each other. If you have theoretical results which cannot be confirmed by experiment, there will always be concerns about that. After all, the purpose of a theory in physics, and its validity, is measured pretty much entirely by how much predictive power it has. Quantum mechanics was considered very inelegant and not particularly beautiful by a lot of the people who came up with it, including Einstein, who famously disagreed with some of the philosophical implications and, perhaps you might say, the overall aesthetics of the theory. But it has become accepted as the true, underlying nature of the universe, or at least the best available description thereof, not because it is neat and tidy, but because of its superior predictive power. Predictive power that, of course, has enabled the development of many modern technologies. For that reason, if you have a very elegant theoretical model, but it cannot make predictions which can be tested by experiment, it's always going to be incomplete and will not necessarily be regarded as established physics. On the other hand, it's perfectly possible for experiments to get ahead of theoretical models. In fact, this was of course how it was for most of the history of science, where people would regularly perform, chemical experiments and reactions and so on, without really understanding how they worked, but just documenting the phenomenon, and the mathematical theories came on much, much later. I mean, you think about the length of time that humanity knew about facts about magnetism and electricity before proper theories of electromagnetism started to be developed by Maxwell and others later on. In this sense, particle physics has been a bit of a victim of its own success. The standard model of particle physics, the theory behind it, which we outlined, was theoretically completed even as early as the 1970s. As a reminder, this is the model that explains most of the elementary particles and 3 out of the 4 fundamental forces in physics. You've got your quarks, your 3 families, getting heavier and more massive as we go on, up, down, strange and charm, top and bottom quarks. Then you have 3 families of leptons that also get more massive as you get up. These are your electron, your muon, your tau particle. They have associated neutrinos with them that are associated with the weak force too. And then you have the force-mediating particles, the bosons. The photon handles interactions that are part of the electromagnetic force. The gluons are associated with the strong nuclear force between the quarks. The W and Z bosons mediate the weak nuclear interaction. And then finally, on top of that, you have the Higgs boson and the Higgs field, which determines the mass of each of these fundamental particles. That's your standard model, the building blocks of the standard model. And from them, you can determine a great deal about how particle physics, and consequently the universe made up of particles, actually operates in practice. Now, as we say, in its own terms, this model has been almost too successful. Particle physics for the last few decades, especially on the experimental side, has included a lot of confirmations that particles predicted by this theory really do exist. For example, the top quarks discovery in 1995, the tau neutrino in 2000, finally the Higgs in 2012. Each of these particles had essentially had properties broadly in line with the predictions of the standard model. And so, although we've got more and more evidence that the standard model is correct, our picture of the theoretical underlying fundamental physics here has not vastly changed due to these discoveries. Meanwhile, though, the theorists, I guess bored, have been developing all kinds of theoretical extensions to the standard model. Now, okay, there are a number of reasons why you might want to do this beyond looking for a grant, mostly due to various dissatisfactions with the standard model, which doesn't explain everything and can't really be all there is to particle physics, at least in the opinions of many of these people. Some of these new theories are guided by this idea of naturalness. The standard model, in their view, is inelegant because it sort of requires you to pluck a whole bunch of arbitrary constants out of the air to explain the masses of different particles, the relative strengths of the different forces, etc. And this is philosophically disturbing and inelegant because you haven't really explained where these numbers come from, and yet they are fundamentally important to, well, the nature of the whole universe, the fact that anything can exist at all. For example, take the mass of the W boson. Off by a tiny amount in either direction, and the nuclear physics of stars is completely different, and life on Earth, at least, would not exist. The ratios of the strengths of the forces, which might seem like arbitrary numbers plucked out of the ether, these things are vital to explaining how structures and stable chemistry, like the ones that we know, can be stable or possible at all. So a theory that doesn't explain where these numbers come from, but just takes them as initial inputs to the theory, is never going to satisfy everyone. It's easy to win the lottery if you know the numbers already. Maybe it's too easy to explain the universe if you let yourself arbitrarily choose and measure all of these constants like they were parameters that were set at the beginning of the game. So then the question becomes, is there a more fundamental theory which can help to explain why these constants are what they are? There are, of course, other questions that you might be interested in. Others are looking for ways to unify this model, and quantum field theory more generally, with gravity, which you'll notice is the fourth force that's not really accounted for in the standard model. And this is the cliched grand problem that theoretical physics has had for a long time now. How do you marry up quantum mechanics and general relativity? We're sick of saying it, but the solution has not been found yet. One or both of the Standard Model and general relativity seems to have fundamental incompatibilities with the other one. This in turn makes modelling the very early universe just after the Big Bang extremely difficult. Now, of course, there are also problems in cosmology, which we've been describing in the recent series, which seem to require, or at least suggest, that new physics beyond the Standard Model could be possible. For example, some have said that if dark matter theories are correct, there may need to be a new type of massive particle to account for the presence and composition of the dark matter. But would that be made up of matter like the matter that we know, or would it be an extension to the Standard Model? That's not clear. Some people have argued that the force driving the expansion of the universe, sometimes referred to as dark energy, that this may require its own particle to explain it. And some other hypothesized particles or other fundamental forces have been appealed to in the past to explain inflationary theories of cosmology. This period of really extremely rapid expansion in the early universe that smoothed it out sufficiently for the distribution of energy and matter to match what we observe today. Now, all of these could potentially be explained, made easier. They kind of suggest, but don't of course observationally prove, that there is physics beyond the Standard Model that maybe we could work out theoretically or probe with these high-energy physics experiments which are aiming to smash together various particles in the hope of creating new ones. So it's possible to create broader theories that include the Standard Model, but also include beyond the Standard Model, or BDSM, physics, in much the same way as special relativity, for example, reduces to Newton's laws of motion when speeds are very much slower than the speed of light. Special relativity therefore basically contains the same physics as Newtonian mechanics does, but only in the limiting case, where you have these slow speeds. In this case of a beyond the Standard Model theoretical model, the Standard Model that we know and love would then be a limiting case, if you like, a corner of this grander theory. The problem has turned out to be that it's possible to create a great many fancy and wonderful and arcane mathematical or theoretical structures which could potentially be true, but which are very difficult to test. For example, many theories contain supersymmetry in them, the idea that every Standard Model particle has a supersymmetric partner particle. But in most of these theories, these supersymmetric sparticles are much heavier than the Standard Model equivalents. This means that, in practice, to produce them in particle physics experiments, we need experiments that probe higher and higher energies. The highest collision energy that the LHC can probe is 14 trillion electron volts. That, by the way, means the energy in the collision is approximately equivalent to 10 to the minus 23 kilograms of mass. Now, to achieve that, you have required a collider with a 27-kilometre circumference. Probing even higher energies, it would generally be expected, would probably require even bigger colliders. But the field of high-energy particle physics has found itself backed into a corner by the success of the LHC and the Standard Model. It's wonderful that the LHC succeeded in confirming the Higgs, but you always got the sense that the real dream and the real goal would be to find some smackwell of evidence of that beyond the Standard Model physics, that brand new physics, rather than confirming decades-old physics. Not that there's not a lot of interesting science to be done in observing and gathering data about things like the Higgs now that we can make them, but it's not going to produce one of those fundamental scientific revolutions that everyone dreams of being involved in, or necessarily is it going to clearly answer those big, outstanding questions in theoretical physics, fundamental physics, or cosmology that we discussed as motivations for seeking physics beyond the Standard Model. The trouble is that a priori, the scientists don't have much to go on. There were good theories as to where to look for predicted particles like the Higgs and the top quark, for example. We sort of knew ranges of the mass that they might be able to produce. The sort of ways of producing these particles were expected. But if you're just looking for some kind of anomaly, something that the Standard Model can't explain, it's a bit of a fishing expedition. Not that there is nothing intrinsically wrong with this way of proceeding or going fishing. Listeners might remember our episode on the efforts that have been made experimentally to directly detect dark matter particles, where we talked about the various efforts to detect any rare interactions between dark matter particles and ordinary matter. There's some of these things are happening underground in massive tanks. Some of them have got these super fine crystals that, if they're struck by anything, would vibrate in a way that can be detected. Things like the Xenon 1-ton experiment that I think is currently being undergone at the moment that's gathering data. You will recall that what they essentially did was it was a process of building ever more sensitive detectors that could find ever rarer collision events, and just kind of hoping that something would crash into this detector and that they'd be able to find out about it. And this has led to tangible advances in physics. Because effectively, eventually, we've combed through all of the potential parameter space. Likely within the next few years, we will have combed through all of the potential parameter space for a certain type of dark matter particle. Likely within the next few years, as these experiments are going on, they will either find dark matter particles through this direct detection, or they will have fished in the entire lake, if you like. They'll rule out being able to find them this way above the background noise of the universe, because the detectors won't be able to be made sensitive enough. So this is also a fishing expedition, but you're ruling out systematically these big swaths of parameter space, like fishing in various areas of the pond, looking for that one valuable koi carp. These huge regions of potential where something interesting might be, but where you don't find anything. And of course this is worth doing, but it presents a bit of a problem when it comes to getting funding. One of the potential routes, and this is controversial, to a successor to the Large Hadron Collider is the so-called Future Circular Collider. This would scale up the collision energy by another factor of 10, producing collisions with up to 100 trillion electron volts. Now, the design of this thing is not really settled yet, but there's some talk of it being 80 to 100 kilometres in circumference and maybe costing 20 to 30 billion. So you can see it's kind of like 5 times bigger. Other improvements get you the energy as well, But 20 to 30 billion is more than the LHC cost. But the problem is that when you're pitching funding for this, there's no guarantee that there will be anything interesting at all in this energy range. And with the standard model looking very complete and unassailable, it's going to be hard for the field to get funding for this kind of second-generation project. And I think it will also be difficult for a crop of excited new young scientists to get involved in the field if they don't think there's anything for them to find. If it looks like an uncertain fishing expedition, that's not necessarily something people want to spend time doing. So there is a potential now for the field to become less interesting, and certainly less exciting than it was in the heyday of the LHC. And this might lead to a long particle physics winter setting in. Like other technological or scientific winters, we've talked about AI winters before, this doesn't mean that there will be no developments at all. Potentially new techniques or methods will be explored amidst frustration with how things are done at the moment. Like maybe scientists will try to go back to mining naturally occurring high-energy cosmic rays for information somehow. Or maybe particle physicists will rely more on astronomical observations for information about particles. Maybe they'll work on new types of passive detector, like the direct detectors for dark matter that we discussed, rather than necessarily relying on these big colliders to produce high-energy particles for study in the lab. But nevertheless, the success of the standard model, and the fact that tantalising experimental hints of BDSM physics have proved hard to find, while the theorists have vaulted potentially a long way ahead of the evidence we can gather, this has potentially meant that the field was facing an impasse. Now, I realise that we've done a whole episode here basically just of context, but I think it's important, before we get on to the next episode talking about these new news stories, to understand where the particle physics and high-energy physics field is, and therefore why these new discoveries are not necessarily just being seen as the sort of obscure or mild curiosities that they may seem to be at a first glance. It's hard to know why people might be interested in some tiny discrepancy in the measure of a single parameter or a single particle, until you realise that it's this tantalising hint of evidence for, potentially, physics beyond what has been established as the theory already. Without that context, it's hard to know what this might mean more broadly for physics. But once you have some awareness of the background, you can start to see why particle physicists are getting very excited about anything that looks like it might potentially be concrete evidence, or at least any sort of line to go down for new physics. After all, it gives the experimentalist something to aim at, something to look to do, and the theorist something to try and theoretically explain, and potentially to restart and kickstart again that virtuous cycle where their theories can guide more experiments again, so that new developments in the field can continue. Right, with all that in mind, next episode we'll talk about these experimental results. Thanks very much, everyone, for listening to this episode of Thermonuclear Takes from Physical Attraction. I appreciate all of your support so much. There's many ways you can support the show. Follow us on Twitter, PhysicsPod. You can follow the Science Podcast Facebook group, which is on Facebook. We have an Instagram, which I don't know how to use and haven't used properly. If you can find that, feel free to follow that. Get some credit for being the most dedicated fan. You can contact us via the contact form on the website. That goes through to my email. I try and respond to the emails that I get, time pending. It's always good procrastination material to answer back to these, so you may get an answer sooner than you think. And it always makes my day when people email me, so I really appreciate that. You can review the show on podcast platforms. On the website, you'll find information about the show, the episode guide for past episodes. We've referred to a few of them, the direct detection of dark matter, the concealing a hadron. Go back and listen to those if you want. They're all available, of course, and always will be. On the Patreon, you can support us. You can get access to the episodes of Cosmology that haven't been released yet, and you can get access to our long series on negative emissions and some improvised episodes that I've done in recent times as well. All of the bonus episodes are available there for a small fee of basically pay what you want per bonus episode. So it's good for times like now. I haven't been releasing many bonus episodes there lately, which means that the fans aren't paying. You're not being subscribed to something that takes money out of your account every month. It's just as and when new content comes up. Thanks to everyone who does that already. There's also a PayPal link for one-time donations on the website. That's another way you can financially support us. But the best way as ever to support us is to tell people who might be interested in the show about the show to listen to it. Review us on iTunes. I think this might be the first closing ambled thing where I've actually said all of the things that I was supposed to say. So I'm pretty pleased with that. That's a good note to end it on. I hope you're all doing well in these horrendous, continually horrendous times. And until next time then, please do. Take care.
Okay.